Okay, so this is theory. This is lecture 18. Okay, it's moving a little bit. Excellent. And so what we're going to do today is we're moving on to chapter 6, which is rational and irrational numbers. So hopefully everyone here has some sense of what rational and irrational numbers are. So chapter 6, rational and non-rational. Okay. What is the first thing I have to prove when we do rational versus irrational numbers?
Is irrational?
Exactly. It's basically a requirement that you have to show square root of 2 is irrational. So theorem, square root of 2 is not a rational number. And depending on which math book you use, they talk about how this distressed a lot of the ancient Greeks. Because you could take a right triangle with sides of length 1, and you can easily construct this. And so you've constructed an irrational length using just rational processes. And so again, we say number is irrational if we can't write it as a ratio of 2 integers. There's a lot of different ways to prove the square root of 2 is irrational. They illustrate a lot of good techniques. A lot of them are pretty similar. Most of them go proof by contradiction. Assume square root of 2 is rational. So the square root of 2 equals a over b. And there's two different things you can now assume about a over b, depending on which type of proof you want to give. Anybody want to give me one of the choices?
They're not both even.
Okay, so a little bit weaker than that is that they're relatively prime.
Sure.
You can say, look, if A and B have any common factors, don't be an idiot. If 5 divides A and 5 divides B, pull that out. The other thing you could do is you could say, I'm going to look at all of the pairs A and B that work, and I'm going to choose the one with smallest b. The proofs are very similar. The argument is almost identical in terms of the differences. It's how you phrase them. Wait, you're wearing a pirate shirt today?
Yep.
Excellent, excellent. So I'm going to choose to do the one where I assume b is the smallest number that works, because this leads to a beautiful technique called the method of infinite descent. And the way it works is you assume you have a solution with a certain minimal property. And then you show you have a solution that's even smaller. Well, if it's smaller, that violates the fact that you had the minimal solution before. This is a great way to solve a lot of problems. Fermat's last theorem, some of the cases are solved by this, not all. Now, of course, for this to work, you actually need to have a minimal solution. Will there be, let's assume square root of 2 is rational. Will there be a ratio a over b with the smallest possible value of b? Yes?
They're 1. Well, is it like an absolute minimum? It can't be less than 1.
Okay, b can't be less than 1. So we know b is bounded from below, because the ratios of integers. B is at least 1. And as long as we have one solution, let's say the solution was 2017. Now all we have to do is check all the b's from 1 to 2017. It's a finite list to check and see if anything else works. So because there's a finite set to look at, as soon as we know that there's one solution, there will be a minimal solution. So choose smallest b. Okay? And now, if we square, we get 2b squared equals a squared. So I'm squaring and cross multiplying. So what can I deduce from this? Yes.
A is even?
A is even. So one way to show this is to be very painful and say, well, A could either be 2m or A could be 2m plus 1. If I square things, A squared is 4m squared. A squared is 4m squared plus 4m plus 1. So if A is odd, A squared is odd. That can't happen. This is essentially what the Greeks were doing, because they were doing it case by case. But we have a nice result. We proved if a prime divides a product, then it has to divide at least one of the factors. So I don't have to go through this. Otherwise, if I do now trying to show the square root of 3, square root of 5, square root of 7, the square root of 7, oh god, I'd have to go through all 7 cases. So we can see why we like the fact that if a prime divides a product, it divides 1. So therefore, 2 divides A, so let's say A equals twice alpha. Then we get 2b squared is 4 alpha squared, or b squared is 2 alpha squared, and now what can we deduce? Yeah, backed by popular demand, it's the same argument we had a moment ago. And now we get b is even, so 2 divides b, so b equals 2 beta. So thus, the square root of 2 is a over b. It's also 2 alpha over 2 beta, or alpha over beta. And so your contradiction can either be a and b were not relatively prime, or you now found a smaller beta. So contradicts minimality. Okay, and so that proves that the square root of 2 is irrational. One of the best colloquia I've ever heard at Williams was 6 proofs of the irrationality of square root of 2. And one of them was giving a proof by Stanley Tenenbaum in the 1950s that was geometric. I was going to be very careful because this is being recorded. I was sitting next to Professor Morgan, who remarked it's a real shame that this proof only works for the square root of 2. And of course, you give your complete undivided attention to the speaker at a colloquium. You would never do anything other than that. A split second, I think, after the colloquium ended, I may have passed Professor Morgan a note with an extension to the square root of 3. You can extend this to other numbers, but not to all square roots. I will give an A+ to anyone in this course who can extend this argument to the cube root of 2, or if you want instead trying to do more square roots, to some of the cases that can't be done. So I'll post the paper. If you want an A+, if you can come up with a new way to apply this. This is a geometric proof. So let's assume the square root of 2 is a over b, and b is the smallest possible. So the proof is looking very similar to how we started. But now we're going to do the argument geometrically. Which is larger, a or b? A, right? Square root of 2 is greater than 1. So I'm going to draw a square of side length a. And so the area of this square is a squared. Well, from what we had before, we also get, 2b squared is a squared. So 2 squares of side length b should have the same area as this square of side length a. Where do you want to put the first square of side length b inside this? You've got 5 choices, or 2 equivalent classes of choices. Where would you want to put?
In the corner?
Yeah, the corner is the most natural place. You could do the center, or maybe even the center of the side, but I think the corner is the most natural thing to try. So we'll put the first one in this corner. Where should we put the second one? We've got 3 choices. Any thoughts?
Opposite corner.
Opposite corner. And if that doesn't work, then we try, an adjacent corner. But if we put it in an opposite corner, something fascinating happens. This is not even close to scale. This square is counted twice. These 2 squares aren't counted at all. The area of this square plus this square is the area of the whole thing. So this region, which is doubly counted, must have the same area as these 2 regions that aren't counted. So we just have to figure out what the lengths of everything are. Okay, what's the length over here? A minus b. So twice a minus b squared, that's these 2 things, must equal this one squared. So now we need to figure out what's the length of that one. So if the whole length is a, and this is a minus b over here, and this is a minus b over here, this length would be a minus twice a minus b. So this length would be a minus twice a minus b. So I think it's 2b minus a. And now we've shown that the square root of 2 is 2b minus a over a minus b. We now have another way of writing the square root of 2 as a ratio of two integers. What do we need to do to finish the proof? We need to do one last thing. What do we need? Yes?
That a minus b is smaller than b.
Yeah, we need a minus b is less than b. So we need to compare a minus b versus b. So this is a versus 2b. Or a divided by b versus 2. We know how to compare a over b versus 2. A over b, by assumption, is the square root of 2. Right? So that means it has to be less than everywhere. And so we now have a smaller denominator. So we win. This is a geometric proof. To get the square root of 3, you use triangles. I think it's something like this, where you have these ones double counted and this one missed. I can't do 4. Anybody know why I can't do 4?
Because the square root of 4 is 2.
Yeah, the square root of 4 is 2, right? Yeah, the method should not work for 4. 5 we can actually get using regular pentagons. 6, I haven't found a way to make hexagons work, but I found a way to make 6 work by taking an even larger triangle and putting in like another row coming in, I think like this, something like that. Haven't been able to get 7 to work. Was able to get 10. So if you notice, we're getting numbers such as 3, 6, 10. Does anybody recognize these numbers? They're triangle numbers. So maybe if I keep using these triangles, I can show the square root of any triangle number is irrational. Now the nth triangle number is going to be n plus 1 over 2. Do you think I should be able to show every triangle number has an irrational square root? What do you think?
Except for that 1.
Yeah.
Except for 1. Okay, I'm definitely happy to throw away 1. So do you think n times n plus 1 over 2 is always irrational? What could we do? So what could we do if we think, n plus 1 over 2 is always irrational?
We could write a computer program.
Yeah, write a computer program. It's like going through values, right? And take the square root and see if all of them are irrational. If you look at this, I want n plus 1. I want those factors. I want one of them to be a square and one of them to be twice a square. If I take n to be 8, I get 8 times 9 over 2, it's 36, which is a perfect square. So somehow the method of proof breaks down. It works for 3, it works for 6, it works for 10. I won't tell you how far it works, but somehow something has to kick in and make it stop eventually, because not all triangle numbers. So to me, there's a lot of interesting stuff going on here. If you can make this proof work to prove the cube root of 2 is irrational, I will give you an A+ for the course. I would love to see this method extended to cube roots. I will give an A. You have to talk to me and negotiate about extending these square root arguments to something new. But if you're able to do that, this is publishable mathematics. I will give an A for publishable mathematics. So there are powers to different perspectives. Okay, so what I want to do now is I want to talk a little bit about how we actually approximate numbers. So how many people here are computer scientists or have taken courses in CS? Excellent, a couple of you. Are you able to work with irrational numbers in a computer? No. What can you work with on a computer?
Binary fractions.
Binaries. You have zeros and ones. You have a finite number of zeros and ones and a finite number of computations you can do on zeros and ones. So a computer cannot access all numbers. It can only access a very small set. And then the question is, how well would you approximate a number like pi if you need to do pi for computation? How would you handle this on a computer? We have to somehow replace pi with something rational and control errors. And so the idea is to try to find the best approximation possible. And so this is a wonderful concept. And so we say P over Q is a, I want to make sure I use the same terminology. They say best approximation of first kind is a best approximation of the first kind to an irrational alpha if alpha minus P over Q is less than or equal to alpha minus A over B for any B less than or equal to Q. The book, I think, phrases it slightly differently, has a strict less than sign here, and then says A over B can't be the same as P over Q. Doesn't really matter. What it's basically saying is, if I fix my denominator and say, I don't want to look at any denominator bigger than 1,000, any denominator bigger than 2017, of all the fractions whose denominator is at most 2017, which one is the closest? If I want to get a really good approximation to pi, can somebody give me a good approximation to pi as a ratio of two rationals? So 314 over 100. Give me another approximation that's a little bit better, still a ratio.
over 10,000.
Yeah. I could do 9, 2, 6, and add another 3 here. It's really not that hard to write approximations to pi. And if I want to get more digits, I just add more terms. So you want to somehow measure how expensive something is. You always want to come up with a metric. What is your metric for this? Well, the bigger the denominator, the more expensive it should be. Think about it working on a computer. The bigger it is, the larger the number, the more expensive the computations. So the book talks about a height function. We're not going to do too much with height functions. The height function is defined as the maximum of the absolute value of the numerator and denominator. So typically, the height of P over Q is the maximum of the absolute value of P, absolute value of Q. And sometimes people use the logarithmic height of P over Q, which would be the maximum of the log of P log of Q. And you might want to do this base 2 rather than base E. The reason is that when I really want to measure complexity, I really care about the number of digits. And if I'm doing things on a computer, I'm not doing things base 10. I'm doing things base 2. So I might want to do these logarithms base 2, but we know from calculus logarithms base E are nicer. There's a constant conversion factor from the two, so maybe I'll just do things in base E. Not going to really make much of a difference. But the logarithm is a really good way to measure how complex a number is. It essentially tells you the number of digits. And the more digits I have, the better job I should be able to do. So the challenge is, if if I only give you a certain size denominator, what's the best approximation you can do? So step one is always to come up with a really bad, inefficient algorithm. Okay? So let's say I want to find a good approximation to pi, and I don't want to use anything larger than 2017. Can somebody give me a way to find it? How can I find a good approximation to pi? Yeah.
Go through each integer up to 2017 and find the best approximation, and
Yeah.
then find the best approximation one, the best approximation.
Try each denominator, and then see what I need for the numerator to get closest. Record how good that is, move on to the next denominator, and boom, 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 boom. It'll run in a finite amount of time. And then I just record and save the result. And if I have a new number, I just do this again. This will work. This will also be horribly inefficient. You know, when we did RSA encryption, we saw the need for speed. We saw that we need to be able to do these calculations quickly. This is not going to work. So we'll talk a little bit about continued fractions. We're not going to go as deep as it goes in the book. Continued fractions give you a mechanical procedure to come up with good approximations. And it also allows us to answer a question. We won't answer it in this class, but it gives you enough tools so that you could answer the question, what is the most irrational number of all numbers? Have we talked about that at all this semester? So give me some candidates for the most irrational. Give me some candidates. Pi. Pi has to be on the list, right? Who else makes the list?
E.
E, absolutely. E's on the list.
Pi.
I'm sorry?
Pi.
Pi, the golden mean on the list, absolutely. What else?
Root 5.
I'm sorry?
Root 5.
I wouldn't put root 5 on the list. I mean, we've got phi. I'm not going to put root 5 on the list if I have phi. But there is another square root that I would put on the list.
Do you like root 2?
I'd put on root 2. I mean, we started with root 2. You know, it might be like a pity inclusion that it has no real chance, but we're just trying to make root 2 feel good about itself, that it can be on the list. Any other numbers you can think of? Maybe the Euler-Mascheroni constant, if you've seen that from the harmonic series, maybe you could put that in. Any physicists here? I don't believe those. All right, so this is a pretty good list. The winner is actually on this list. The most irrational number is one of these 5. Anybody have any idea?
It's E.
I'm sorry?
I'd say it's E.
It is not E. So it's getting a little bit easier now to get which one is the most irrational. It's phi, the golden mean. So it turns out the continued fraction of phi is all 1s, and the larger digits you have, the better approximations you have, which we'll see. And so it turns out, what do I mean by most irrational? I mean, when I try to find the best approximation, which one has the best approximation, which is furthest from the truth? So there are certain numbers that have really good approximations. We will eventually talk about Liouville numbers. There's a lot of different ways of writing down Liouville numbers. This is one of my favorites. The sum n goes from 0 to infinity, or if you want, maybe we'll go from 1 to infinity, of 10 to the negative n factorial. So this is a number that has huge deserts. It's 1/10. What's the next term in the sum?
1/100.
1/100th. Next would be 1/10 to the 6th, then 1/10 to the 24th, then 1/10 to the 120. You know, talk about huge deserts of zeros before you get any action in the decimal expansion. If you truncate this, your error is just a little bit more than 1/10 to the 120. These numbers are extremely well approximable. And what we will show is that these numbers are in fact transcendental. So one of the strange things you can do in mathematics is you can often prove something exists without knowing any examples. And so there are different types of irrational numbers. So we have what's called the algebraic numbers. You're a root of a polynomial with integer coefficients. And polynomial always means finite degree polynomial. So somebody give me an example of an algebraic number. Square root of 2. So, in fact, all square roots of integers are algebraic. In fact, all real numbers are algebraic. So all rational numbers are algebraic. You know, x minus p over q, is that a polynomial with integer coefficients? No, but we can fix it. So somebody who hasn't spoken, what polynomial is related to this that has integer coefficients?
Qx minus p.
Yeah. This is the same as qx minus p equals 0. I can always just clean the denominators. So this shows you that every rational number is algebraic. Square roots are algebraic. Things like the square root of -1i is algebraic. It is a big theorem that numbers like pi and e are transcendental. We could prove the transcendence of them. Transcendental is not algebraic. If not algebraic, then you're transcendental. And so we will definitely do enough so that if you want to, you can read the proof that e and pi are both transcendental. One of my favorite theorems is we know either e plus pi or e times pi is transcendental. We don't know which, but we know at least one of the two is transcendental. We're pretty sure both of them are transcendental. We can actually prove at least one of them is transcendental. What's fascinating, how many of you have done Cantor's diagonal argument? Just trying to get a sense of, okay, how many of you have taken real analysis? Oh, so some people did real analysis without doing Cantor's diagonalization argument?
Well, I took a flat fail.
Okay, I'm not going to say more because the camera's rolling. Okay, so, I'm sorry?
I don't know if that makes a difference. Maybe we still should have covered it.
I've never taught real analysis, so I do not know what is covered. But you often see, have you done countable versus uncountable sets? Mm-hmm. So, okay. So the rationals are countable. The algebraic numbers are countable. The transcendental numbers are uncountable. So Cantor proved that there are uncountably many irrational numbers. So that means they must be transcendental numbers. But the problem is, okay, great, almost every number is transcendental. Can you give me an example? Well, no, but I can show you almost any number is transcendental. I'd like an example, please. So it turns out the Liouville number over there is transcendental. And we will actually be able to prove that that is transcendental when we get to chapter 7. So we can definitely do that within this class. And in fact, there is a tweak of that that allows you to construct uncountably many transcendental numbers. So we can at least prove an explicit existence of uncountably many transcendental numbers by enumerating them. What Cantor's diagonalization argument, if you've seen, does is just says there are uncountably many transcendental numbers. Almost all numbers are transcendental, but it doesn't give you one. This will actually give you one. All right. So let's go back to what we have over here. So a best approximation of the first kind is we want this to be smaller than all others. We want to figure out how do we want to measure how good an approximation is. And it should be something in terms of the denominator. Now, let's walk before we run. Say P over Q is a best approximation to alpha. What can you tell me about how close P over biggest result you can think of.
It's less than 1 over q.
It's less than 1 over q. Because I'm walking in steps of size 1 over q. So here's alpha. Here's 0. Here's 1 over q. Here's 2 over q. Here's 3 over q. I'll start here with a Boston accent. I keep walking in steps of 1 over q. If I'm before alpha, and I go past alpha, I've moved 1 over q. I'm not going to exactly land on alpha because alpha we're assuming is irrational. So I've got to be within 1 over q. So no matter what, I can do an approximation at least this good. The question becomes, can we do better? Can we do 1 over 2q, 1 over 3q? That's only fixing it by a constant. I want to have something fixing with q's. Can I do 1 over q log q? Or 1 over q log q? Or 1 over q squared? Or 1 over q cubed? Or 1 over q to the 4th? It turns out, if you can approximate a number extremely well by rationals, it's transcendental. That's what we'll see with Liouville's theorem. That any number that is extremely well approximated by rationals is transcendental. So what we're going to do now is we're going to do Dirichlet's theorem. Have we done the pigeonhole principle in this class? Or we've not done pigeonhole yet? Okay. There's a non-trivial intersection between some of the material in this and some of the material in my problem-solving class, and I always forget exactly what we've done. So Dirichlet's theorem. If alpha is irrational, then there exists infinitely many relatively prime p and q such that alpha minus p over q is less than 1 over q squared. So that tells us we can get a lot closer than just the naive estimate would give us. And the key ingredient in the proof is the pigeonhole principle. Most of you are probably never going to be approximating irrationals by rationals in the rest of your life. But the pigeonhole principle, that's something you could possibly use. It's one of the best proof techniques we have. So there's a lot of ways to phrase the pigeonhole principle. It's also sometimes called the box principle or Dirichlet's principle. It's amazing how useful this is. So imagine you have n boxes. And you have a pigeon gun. Anybody seen the Despicable Me movies? Where he has, I think, the gun that shoots squids? Similar concept. Right? We have a pigeon gun. And we have n plus 1 pigeons. And we shoot the pigeons into the boxes. And each pigeon is shot into a box. But I have complete freedom in terms of which box I shoot the pigeons into. Okay? So if you haven't seen the pigeonhole principle before, I'm shooting n plus 1 pigeons into n boxes. What can you tell me must be true? So if you haven't seen this before. Yes?
At least one box will have 2 pigeons.
Good. At least one box has 2 pigeons. Because if not, then each box has at most 1 pigeon, and that can only account for n pigeons. Another way of looking at this is at least one box has the average numbers of pigeons per box. In pigeonhole problems, there are 2 issues. The first is figuring out what the boxes are. The second is figuring out what the pigeons are. Usually one of those 2 is hard. Sometimes it's pretty straightforward what the pigeons in the boxes are, but that's what you have to really think about. What are my objects, and how do I want to classify them as being equivalent? If you look at a clock, which you're not doing right now because this lecture is fascinating and you're completely devoted to this, but your clock has 12 hours. So if I give you 13 times, what can you say about those 13 times?
least one is going to be the same one.
At least one is going to be in the same hour as another. You know, at least two of them have to fall with the same leading hour. And so if you talk about times on a clock, it's pretty clear I'm looking at things mod 12. I'm looking at things that remainder when I divide by 12. So we're going to use Dirichlet's pigeonhole principle to show that we can approximate very well. Okay? So we want to show that we can do this infinitely often. And we want our P and Q to be relatively prime. Well, if P and Q are not relatively prime, what's really going on? I could get infinitely many approximations, but I'd be, if it's, P over Q, 2P over 2Q, 3P over 3Q, the approximations aren't getting better. And my denominator would then be going from Q to 2Q to 3Q, and I wouldn't be able to do this. So if I just rescale my P and Q by the same amount, it's not going to get me a better approximation. I need to really use different ones. Okay. So proof. So fix a big number Q, and then consider n alpha mod 1 for n going from 1 to Q plus 1. So what n alpha mod 1 means is I multiply alpha by n, and I look at the fractional part. So if my alpha is pi, 1 pi mod 1 would be about 0.14159. If I look at 2 pi, it would be 6.28 dot dot dot, so it would be about 0.28 when I look at it mod 1. Okay? So I've got Q plus 1 objects. How many boxes do I want? Yeah, because I want to somehow use a pigeonhole principle. I want to somehow say two of these objects are in the same thing. What do you think my boxes should be? Let's see, and without loss of generality, we might as well assume alpha is in the interval 0, 1. Because otherwise, I just subtract off, an integer from it. And that's not going to affect the quality of the approximations. So I've got Q plus 1 objects. I've got to figure out what I want my boxes to be. So here's 0, here's 1. I don't know exactly where alpha is. Alpha is somewhere. What do you think I want my Q boxes to be? Any thoughts? Yes.
Boxes of size 1 over Q.
Yeah. So what should be the first box?
1 over Q, or from 0 to 1.
Yeah, from 0 to 1 over Q. Excellent. And then 2 over Q, and then 3 over Q. So these are my boxes. And at least two of these numbers have to land in the same box. So assume n alpha mod 1 and n alpha mod 1 are in the same box. So I can write this maybe as n alpha minus a1, to make it now a number between 0 and 1, and m alpha minus b, no, I'll do a2, in the same box. Right? So what's the difference between these two? So if I look at n alpha minus a1 minus m alpha minus a2, how can it be? At most 1 over q. Which q? Well, there's only one q in the problem. I can now rewrite this as n minus m alpha minus a1 minus a2 is thus equal to 1 over q. So I'll let this be my q, and I'll let this be my p, and what we would get is Q alpha minus P is less than equal to 1 over Q. So you get alpha minus P over Q is less equal to 1 over Q cubed. Close. We wanted to get 1 over little q squared. We have 1 over little q big Q. What can you say about little q and big Q? What do we know about little q?
It's at most big Q.
It's at most big Q, because we have n ranging from 1 to q plus 1. So the largest n minus m could be is if 1 is q plus 1 and 1 is 1, so the difference is at most q. So we know 1 less than equal to q less than equal to big Q. So we get alpha minus p over q is less equal to 1 over q squared. Oh crap, I said it was supposed to be strictly less than I have less than or equal to. So close. Is there any way I can go from less than equal to strictly less than? I mean, it's not that big of a deal. But we have a guest here today. It would be horrible for me to prove the wrong theorem, and he goes back to Chicago. The Tribune publishes this paper about Williams professors can't read mathematics and prove the wrong things. How can I change the less than or equal to strictly less than?
Increase Q.
I'm sorry?
Increase big Q.
I could increase big Q. What would it mean if it was exactly equal? So if alpha minus p over q is exactly 1 over q squared, how many possibilities are there for alpha?
1, right?
2.
For Q, yeah.
Right? I could either add 1 over q squared to this, or I could subtract. What kind of number would that force alpha to be?
Rational.
Rational. But we know alpha is irrational. So I can erase that. Because it's irrational, it can't be exactly equal over here. So the only thing now is, can we do this infinitely often? Maybe we keep getting the same little q every single time. That would be terrible. But the thing is, if we keep getting the same little q every time we do this, well, we also know that this is at most 1 over big Q. And so just take big Q so large that it's going to be less than whatever this difference is, and that will get you a new approximation. So you can get infinitely many approximations from this. Question or no? Okay.
No.
So we do get infinitely many. So let big Q go to infinity. Can't always get old approximations, which means you'll always get new approximations. So we will get a string of numbers. So what this tells us is we can approximate any irrational to within 1 over q squared. What's the next question you should ask? We did 1 over q. I mean, 1 over q was trivial. So let's top, subsidize 1 over big Q. So getting an approximation of 1 over q wasn't that bad. This was what, about 10 minutes of work. With 10 minutes of work, we got 1 over q squared. What if we're willing to devote an entire class? Or maybe even a week?
1 over Q cubed.
Could we get 1 over q cubed? What if I'm willing to spend 3 years in graduate school? Could we get up to 1 over q to the 4th?
You get 1 over Q to the end.
Could we get 1 over q to the end? Could we get 1 over q to the q? Where it's getting even better as you go. Turns out, no. For a general irrational number, this is essentially the best you can do. The only real improvement you can do is you can fix this a little bit by putting, I think, a square root of 5 in the denominator. What does the square root of 5 remind you of? We've heard it today already. The golden mean. The golden mean is 1 plus root 5 over 2. You can fix this. This is Hurwitz's improvement. where he improves it by putting a square root of 5 down below. There is a wonderful, absolutely wonderful theorem called Roth's theorem, and Roth got the Fields Medal for this result. If alpha is algebraic and irrational for any epsilon greater than 0, there are only finitely many solutions to alpha minus p over q is less than 1 over q to the 2 plus epsilon. And one of your homework problems is to actually use this to show that there can only be finitely many solutions to a special elliptic curve. So these ideas of how well you can approximate numbers, you can actually convert this to counting solutions. That's one of the biggest things we do as number theorists, is we want to count how many solutions are there to something. This allows you to know finitely many. You'd love to replace finitely many with something more specific. How many is finitely many? Right? If I tell you only finitely many people will fail the final, this is not really helpful. Right? You want some idea of what does finitely many mean. And that's one of the problems with stuff like this, is these are often hard to make precise. If something is infinite, one thing happens. So something must be finite, but we don't know how big finite can be. So for the next time, we'll start a little bit with continued fractions. We'll talk a little bit about numbers that can be well approximated. So imagine I could approximate my number alpha by 1 over q cubed infinitely often. What can you deduce?
It's not algebraic and irrational.
It's not algebraic and irrational. And so this becomes a way to construct certain types of transcendental numbers. Now the other thing is always how much math do you want to use to prove a theorem. Your Roth's theorem, this is the tactical nucleus strike. This is a Fields Medal result. It is in the analytic number theory textbook that I wrote with a colleague. It is the worst chapter, I think, in the book to read in terms of just going through all the technical details. You have enough mathematics to understand that chapter if you want. It's just a long, involved calculation. There's a much easier result due to Liouville that talks about an algebraic number of degree d. You can't approximate it better than 1 over q to the d. And then you can use that to show that if you can approximate a certain number extremely well, it must be transcendental. So Roth's theorem gives you a faster proof, but it's a lot more prerequisites. So what we're going to do, since this is an introductory course, is we'll prove Liouville's theorem. We will show that an algebraic number of degree d cannot be too well approximated. And we'll actually get to use a result from calculus. So it's always nice to see, the stuff you've done in other courses useful. All right, so this is a good place to stop. By Wednesday or Friday, you will know enough so that I can pass out the second midterm. And again, I will give you a similar long period of time to take it at whatever time works best for you. All right. MathStat monthly dinner tonight.